You know, when you or I sit down to play a brand new video game for the very first time, we usually have like some kind of context built in, right?
Absolutely, yeah.
Like we know what a controller is, we know that uh, glowing red obstacles are probably bad and shiny gold coins are usually good.
Right, we bring a lifetime of intuition into that completely new environment.
Hmm.
The human brain, I mean, it simply doesn't start from a blank slate.
Exactly. But imagine having absolutely zero context. Like you don't know what a screen is, you don't know what a button does.
You have no concept of winning or losing.
Right. Or even existing in a virtual space at all. You are just blindly flailing around in the dark. So how do you go from that state of total ignorance to not just playing the game, but completely dominating it?
It's a huge leap.
It really is. And you do it with a concept called Q-learning. Welcome to today's deep dive. Our mission today is to shortcut your journey to understanding one of the absolute core mechanisms behind how machines actually learn to make decisions.
And it's a fascinating mechanism.
We are looking at a comprehensive Wikipedia article on Q-learning, and by the end of our time together, you are going to understand exactly how AI pulls off this magic trick without needing a degree in computer science.
The transition from blind guessing to strategic mastery really is elegant once the underlying machinery is exposed. I mean, it all boils down to how a system mathematically learns to assign long-term value to its immediate choices.
Okay, let's unpack this, because before we dive into the math, I want to ground this in the physical world to explain what reinforcement learning actually is, since Q-learning is like a specific algorithm operating under that larger umbrella.
Right, it's a subset of reinforcement learning.
Yeah. And the source lays out four basic building blocks.
Right.
We have an agent, which is our AI learner. We
Yeah.
have a set of states, which represents the specific situation the agent is currently in.
Mm-hmm.
We have actions, which are the moves the agent can make. And finally, we have a reward, which is simply a numerical score the agent receives after taking a specific action.
Those four pillars create the entire foundation. And the defining characteristic of Q-learning within that framework is that it is model-free.
Model free. What does that mean exactly?
It means the agent does not require a pre-existing map or an overarching model of its environment. It figures out the rules of the universe entirely on the fly through trial and error.
Oh, wow. So it's just guessing at first.
Exactly. If a certain action in a certain state yields a high reward, the agent learns to favor it. And that brings us to the Q in Q-learning, which simply stands for the quality of an action taken in a given state.
The quality. Okay, so it is constantly computing the expected reward of every move.
Precisely.
The source uses a really relatable example to explain this: the daily commute of boarding a train. Like, let's look at how an AI would approach getting on a subway car. Let's say the reward we want is measured by the total time you spend boarding, and you obviously want that number to be as low as possible. Your cost is your time.
It is a scenario most people have faced. You know, you are standing on the platform, the train arrives, the doors open. What is the optimal move?
Right. So day one, the agent tries the forceful strategy. The doors open and it immediately pushes forward. The initial wait time is 0 seconds.
A very aggressive agent.
Very. But because the train is crowded with people trying to get off, the agent spends like 15 seconds awkwardly fighting its way past departing passengers. So the total cost for that forceful action is 15 seconds.
A highly inefficient strategy, though, one you see humans employ every single day in major cities.
Definitely, I've been that person.
Right.
But then on the next day, the algorithm forces a random choice, a phase the source calls exploration. The agent decides to try a different action.
Have to explore to learn.
Yeah. So it decides to stand back and wait for the departing passengers to clear out. This is the patient strategy.
And in the very short term, this looks like a worse decision.
Mm-hmm.
I mean, the immediate wait time goes from 0 to 5 seconds.
Right, it's just standing there. But because the path is now entirely clear, the agent spends 0 seconds fighting its way onto the train. The overall cost is just the 5 seconds of waiting.
Which is a huge improvement.
Huge. Through forced exploration, the agent experiences this revelation. Even though the initial action of waiting had a higher immediate cost, the overarching long-term route is vastly superior.
What's fascinating here is how the underlying math encodes that realization by shifting its focus. The agent's goal is to maximize total reward, not just immediate reward.
So it's looking ahead.
Exactly. It calculates the quality of a state-action combination by adding the maximum attainable reward from future states to whatever reward it is getting right now.
So it's not just seeking an instant dopamine hit. It's almost calculating the compound interest of its moves. It's asking, does walking through this train door put me in a physical position where my next 5 moves will be highly rewarded?
That concept of compound interest is a great way to visualize it. It learns the potential of an action by weighing the expected values of all the future steps that will cascade from that single choice.
But if it's just wandering around a train station without a map, how does it actually update that math in its head? Like, how does it weigh an old belief against a new discovery?
That happens through the algorithm's engine, specifically the Bellman equation.
Okay.
We don't need to write out the mathematical formula, but its function is essentially a simple value iteration update. Whenever the agent takes a step and learns something new, the equation calculates a weighted average.
So it mixes them together.
Right. It takes the old value the agent believed to be true and blends it with the new information it just discovered.
And the programmer has a few levers they can pull to control exactly how that blending happens, right? The first one the source mentions is the learning rate, represented by the Greek letter alpha. And this operates on a scale from 0 to 1.
Correct. The learning rate dictates how aggressively the AI overwrites its old knowledge.
Yeah.
If a programmer sets the learning rate to 0, the agent learns absolutely nothing from new experiences.
Oh, wow.
Yeah, it relies exclusively on whatever prior knowledge it already has.
It becomes a brick wall. Like, you could show it a faster way onto the train 100 times and it would just ignore you.
On the other end of the spectrum, if the learning rate is set to 1, the agent considers only the most recent information and completely discards anything it learned in the past.
So it just has no memory at all.
It becomes entirely reactive, jumping from one new possibility to the next without building a foundation of knowledge.
That seems bad, too.
It is. In practical applications, developers often use a constant lower learning rate, something around, say, 0.1, to allow the AI to build a steady, reliable memory while still adapting to new tricks.
That makes total sense. Now, the next lever the algorithm uses is discount factor, represented by gamma. The source says this determines the importance of future rewards.
Yes, the discount factor.
So wait, so if I set the discount factor to 0, the AI only cares about the reward it gets in the very next second. Like, it's basically short-sighted.
Exactly. The source actually uses the term myopic for that exact condition. A discount factor of 0 means the AI will only ever optimize for the immediate step. As you increase that factor closer to 1, the agent begins to strive for long-term, delayed gratification. However, there is a mathematical danger zone here.
The danger zone.
If the discount factor reaches or exceeds 1, the formula essentially breaks.
Why does it break? Because it's suddenly valuing a reward 10 years from now just as highly as a reward today.
Worse than that, if the environment doesn't have a definitive final state like a guaranteed end to the game, the action values can diverge to infinity.
Oh, man.
The AI gets stuck in an endless loop of adding up future potential rewards that it will never actually reach, and the learning process becomes completely unstable.
It just crashes.
Pretty much. Developers often start with a lower discount factor and cautiously increase it to accelerate learning safely without triggering that infinite loop.
There's one more crucial lever we need to talk about before the AI can start exploring, and that's the initial conditions, or Q0. Since the AI starts with a completely blank slate, the programmer has to assign some kind of arbitrary starting value to every possible move before the game begins.
And those initial values are incredibly powerful because they can be used to artificially manipulate the AI's behavior.
How so?
The source details a technique called optimistic initial conditions. This is where you assign starting values that are significantly higher than any reward the agent could realistically achieve.
Oh, I see. So the AI takes its very first action, receives a normal reward, and thinks, wow, that was incredibly disappointing compared to what I expected. I better go try all these other unexplored options because they still have those massive starting scores attached to them.
Exactly.
It's a psychological trick to force the machine to explore.
It really is. It acts as a built-in mechanism to prevent the agent from finding one mediocre strategy and stubbornly sticking to it forever.
That's brilliant.
And the article also notes a fascinating parallel to human psychology here. There is a model called Reset of Initial Conditions, or RIC. In this model, the first time an action is taken, the actual reward received is used to set the baseline going forward.
Okay, so resetting expectations.
Right. And the source points out that this specific mathematical model predicts human behavior in repeated binary choice experiments, far better than assuming humans operate on arbitrary conditions.
So we clearly share a bit of that underlying math in our own brains when we're exploring our options.
Yeah.
But as I'm picturing this giant spreadsheet, this Q table with every possible state and every possible action, a massive flaw jumps out at me.
What's that?
Keeping a table of every state is perfectly fine for a simple grid maze or a subway platform with 3 doors. But the real world is infinitely complex. Like, if I move my arm 1 inch, that's a new state. If I move it half an inch, that's another state.
It's continuous.
Yeah. How does a computer's memory not just immediately melt down when faced with an infinite universe of choices?
That phenomenon is known in computer science as the curse of dimensionality.
The curse of dimensionality sounds intense.
It is a major hurdle. As the number of variables increases, the sheer volume of possible states grows exponentially. The likelihood of an agent randomly visiting a specific state and trying a specific action becomes practically zero. Standard Q-learning tables simply cannot handle the infinite nature of the physical world.
So how do we fix it? The source details a couple of fascinating workarounds. The first is a concept called quantization. To explain this, let's use the source's example of trying to teach an AI to balance a stick on its finger.
Ah, a classic continuous physics problem. To understand the state of that system at any microsecond, the AI needs a 4-element vector.
A 4-element vector, right?
It has to track the position of the cart or finger in space, its velocity, the angle of the stick, and the angular velocity of the stick.
But the exact angle of that stick could be infinitely detailed. It could be leaning at 1.5 degrees or 1.5 degrees or 1.55 degrees, going on forever. A spreadsheet tracking every single decimal point would require infinite memory.
Quantization solves this by grouping those infinite ranges of values into discrete buckets.
Okay, so instead of the AI trying to memorize the exact atomic angle of the stick, it just throws the data into a bucket labeled near or far or leaning left or leaning right. It shrinks an infinite universe down into a manageable set of categories so the brain doesn't melt.
Exactly. It creates an artificial grid over a continuous world. But for truly massive, complex problems like driving a car or analyzing a video feed, even quantization isn't enough.
There are just too many buckets.
Right. That is where function approximation comes into play. Instead of building a table of discrete buckets, you use a secondary system to generalize past experiences to unseen states.
Meaning, if the AI encounters a situation on the road that is only slightly different from one it has seen before, it doesn't need to start from scratch. It uses the approximation to guess what the quality of its next move will be.
That approximation is frequently handled by an artificial neural network. However, the article highlights an alternative method, integrating fuzzy rule interpolation, or FRI.
Now, fuzzy rules sound inherently unscientific to me, but they actually solve a massive problem with neural networks, right? Because neural networks often act as a black box.
They do, yes.
Like, the AI might make a brilliant decision, but we have absolutely no idea how it arrived at that conclusion.
And a black box can be dangerous in critical applications.
Yeah.
The advantage of using sparse, fuzzy rule bases for function approximation is that it keeps the AI's internal logic transparent and human-readable.
Oh, that's really important.
Instead of millions of hidden weights in a neural network, FRI generates rules like, if the stick is leaning slightly left and moving moderately fast, then move the base slightly left.
So we can actually audit the AI's thought process while still allowing it to handle massive, continuous environments. It's the best of both worlds.
It allows the system to remain understandable while navigating spaces that would otherwise succumb to the curse of dimensionality.
Okay, so we've explored the core mechanics. We know how the Bellman equation updates its beliefs, how the learning levers manipulate its behavior, and how function approximation allows it to tackle infinite spaces. But, why didn't we see AI dominating the world decades ago? Like, where did this actually lead historically?
Well, the formal introduction of Q-learning is widely credited to Chris Watkins, who presented it in his 1989 doctoral dissertation, Learning from Delayed Rewards.
1989.
Yes. And a few years later, in 1992, Watkins and Peter Dayan published a formal convergence proof. They mathematically proved that given enough time and exploration, the algorithm will absolutely find the optimal policy.
But the timeline has a hidden gem here. The source highlights a fascinating precursor that happened a full 8 years before Watkins' dissertation back in 1981.
A system called the Crossbar Adaptive Array, or CAA, created by S. Bozanovsky. At the time, the challenge was framed as delayed reinforcement learning, but the CAA was solving the exact same problem.
The architecture is what really surprised me. It wasn't just a vague theoretical precursor, it was practically a blueprint.
The similarities are striking. The CAA used a memory matrix that functioned identically to a Q table. It introduced the concept of computing state values vertically and actions horizontally.
Wow.
And perhaps most interestingly, it borrowed the term secondary reinforcement from animal learning theory to model how the value of a successful state is mathematically backpropagated to previously encountered situations. It was a pioneering demonstration of what would eventually become Q-learning.
And when you take those foundational concepts from the 80s and 90s and combine them with modern computing power, you arrive at 2014. Google DeepMind patents an application called Deep Reinforcement Learning, or Deep Q Learning.
A massive breakthrough.
They point this new architecture at classic Atari 2600 games, and the AI doesn't just figure out how to play them, it plays them at expert human levels, operating entirely from the raw pixels on the screen.
DeepMind achieved this milestone by using a deep convolutional neural network to represent the Q function. But pairing Q learning with powerful nonlinear neural networks introduces a critical instability.
This goes back to how the AI receives its data, right? If an AI is playing a video game, the frames it sees are highly correlated. Like if it is moving left for 3 seconds, it's just seeing a sequence of moving left images.
And if the neural network is only learning from that immediate sequential feed, it begins to overcorrect. A sequence of moving left might cause the network to drastically alter its internal weights, essentially forgetting how to move right.
Oh.
The learning collapses.
So how did DeepMind fix the memory collapse?
They implemented a biologically inspired mechanism called experience replay.
Experience replay.
Instead of only updating its beliefs based on the very last frame it saw, the system constantly stores its past actions in a memory bank. During the learning phase, it pulls a random sample of those past experiences, a mix of moving left, moving right, winning and losing, and learns from that shuffled deck.
Wait, really? So to keep the neural network from becoming hopelessly biased by its immediate surroundings, the AI essentially sits around reminiscing about a random assortment of its past lives. It breaks the sequence so it doesn't get tunnel vision.
Shuffling the deck removes the correlations in the observation sequence. It smooths out the data distribution, which stabilizes the neural network enough to allow it to master the Atari games.
But even with experience replay, the AI still had a tendency to trip over its own feet in noisy environments. The article points out a persistent flaw where standard Q learning overestimates action values, drastically slowing down the learning process.
The root cause of that overestimation lies in a structural flaw of the original math. Standard Q learning uses the exact same mathematical function to select an action and to evaluate how good that action was.
Okay.
It inherently assumes that the highest estimated value is the most accurate. In an environment with random noise, a lucky spike might cause the AI to think a terrible move is actually brilliant.
You described this earlier off mic as letting a student grade their own test. Like, they're inherently going to be biased toward their own answers. So what's the structural fix?
The fix is an algorithm variant called double Q learning. You essentially split the AI's brain. You create two separate, independent value functions, let's call them QA and QB. You train them symmetrically using entirely separate sets of experiences.
So they are learning independently. How do they interact when it's time to make a decision?
When the agent needs to evaluate a future state, it uses QA to select what it thinks is the best action. But it doesn't let QA grade itself. It uses QB to evaluate the actual value of that selected action.
Oh, that's clever. It creates a system of checks and balances. QA says, I think jumping right is the best move, and QB checks its own independent notes and says, hold on, my data says jumping right is actually terrible. It completely separates the decision maker from the evaluator.
It neutralizes the overestimation bias. If we connect this to the bigger picture, when double Q learning was eventually combined with deep neural networks in 2015, the resulting architecture, known as double DQN, vastly outperformed the original Atari playing algorithms. It proved that by separating the selection and evaluation processes, AI could consistently conquer incredibly complex, noisy environments.
Which brings us back to you, the listener. We've gone from a theoretical grid maze to mastering Atari. But these mechanisms aren't just abstract math, they mirror how we process the world.
They absolutely do.
Next time you are trying to learn a completely new skill like a new language, a complex piece of software, or a new sport, ask yourself what your internal learning rate is. Are you operating with a rate of 0, stubbornly ignoring new feedback because you think you already know best?
Or are you operating at a rate of 1?
Exactly.
Yeah.
Are you frantically throwing out your foundational basics every time you see a new trend on social media? Finding that careful mathematical balance between retaining old wisdom and absorbing new discoveries is quite literally the secret algorithm to mastering the unknown.
The source text does leave us with one final fascinating complication to ponder, found in a brief section on multi-agent learning.
Oh, yeah. This part is wild.
Every scenario we have discussed today assumes the agent is alone. It assumes the environment is passive, just waiting to be solved. But what happens when you introduce multiple Q-learning agents into the exact same environment?
It stops being a solo puzzle.
The entire foundation shifts. If a single agent learns the optimal path by assuming the world around it is static, how does it cope when the environment itself is constantly reacting? The other agents are simultaneously exploring, updating their own Q tables, and changing their behaviors based on what you do. The fixed mathematical horizon vanishes.
It transforms from a static maze into a chaotic ecosystem. You go from a blank slate, flailing in the dark, to not only learning the rules of physics, but having to anticipate the psychology of every other machine learning right alongside you. It's a complex game of digital chess, and definitely something to ponder long after this deep dive ends.